In this video, I'll show a shortcut for solving Kirchhoff's law's problems. This method works for circuits with 3 branches that have batteries and resistors in them, such as the one shown on the screen, and when the goal is to find the 3 unknown currents. This is one of the most commonly encountered problems when applying Kirchhoff's laws in introductory physics. The circuit you are working on might look different from the one shown on the screen. For example, it may have more or fewer resistors or batteries. You may also have to imagine bending or stretching the wires until the circuit has a sideways figure 8 configuration, like the one you see here. But this method should work as long as it has 3 branches. The shortcut equations can be useful when you have a limited time to solve a problem, and you are not required to go through each step of Kirchhoff's laws in details. The equation can also be useful for checking your work and catching mistakes. However, there are some limitations. First, the shortcut equations cannot be used for other circuit configurations, such as circuits with more than 3 loops, or if they have other circuit elements, such as capacitors. Also, since the shortcut would allow you to find answers without going through each step of Kirchhoff's laws, they can prevent deeper understanding of how the circuit works. The shortcut equations are based on the solutions to this circuit. I will call the branch on the left branch 1, the one in the middle branch 2, and the branch on the right branch 3. Notice that each branch has 1 battery and 1 resistor. All 3 batteries have their positive terminal facing upward, and all 3 currents are flowing upward. This becomes important later. Here's the shortcut equation for I1. Although I am not going to prove it, you can get this equation by applying Kirchhoff's laws to this circuit. If I know the EMFs, or voltages, of the 3 batteries, and the resistances of the 3 resistors, we can simply plug in the values to find the current. Because of the symmetry of the system, we can get the expression for I2 from the expression for I1 by performing a cyclic permutation. In a cyclic permutation, you replace subscript 1 with 2, so I1 becomes I2, E1 becomes E2, and R1 becomes R2. Likewise, you replace subscript 2 with 3, and also subscript 3 wrapping around to 1. You get the expression for I3 by performing another cyclic permutation on the expression for I2. For this reason, you don't need to remember all 3 equations. You just need to know one of the 3, and you can get the other 2 using cyclic permutations. Let's see how we can use the shortcut equations to find the 3 unknown currents in this circuit. Notice how this circuit has 3 branches, which means that we can use the shortcut. We'll assume these values for the EMFs or the voltages of the 4 batteries and the resistances of the 5 resistors. Let's begin with the battery in branch 1. There's only 1 battery in this branch, and it has voltage EA. Because this battery has its positive terminal facing upward, just like the corresponding battery in the circuit that was used to find the shortcut equation, this implies we can say that the value of E1 is equal to EA, or 2 volts in this case. Let's consider the battery in branch 2. There's only 1 battery in this branch, and it has voltage EB. Because its positive terminal is facing downward, which is the opposite of the direction of the corresponding battery that was used to find the shortcut equation, we can say that the value of E2 is negative of EB, or negative 3 volts. In branch 3, there are 2 batteries, EC and ED. When there are multiple batteries, we must add their voltages while keeping track of their orientations. In this particular case, EC has its positive terminal facing upward, while ED has its positive terminal opposing it, so E3 is equal to EC minus ED, or negative 1 volt. Let's now think about the resistors. We can find the resistance in each branch by simply adding all the resistances in that branch. So in branch 1, we add RA and RB, and this is equal to R1, or 3 ohms. Branch 2 has only 1 resistor, RC, so R2 is equal to RC, or 3 ohms. Finally, branch 3 has 2 resistors, RD and RE, making R3 equal to RD plus RE, which is 9 ohms. Here's a summary of what we found. We can now plug in these values into the shortcut equations and find that I1 is equal to 0.86 amperes, I2 is equal to negative 0.81 amperes, and I3 is negative 0.048 amperes. Before we end, let's think about the directions of the currents. In deriving the shortcut equations, it was assumed that all three currents flow upward. Because I1 turned out to be positive, this implies that the actual current flows upward. On the other hand, I2 and I3 are both negative, so their actual directions are both downward.